Honored to introduce our keynote speaker, Hillery Hunter from IBM. Hillery Hunter is CTO of IBM Cloud, responsible for technical strategy for IBM's cloud native and infrastructure offerings. She received her bachelor's, master's, and PhD from the University of Illinois at Urbana-Champaign. Prior to her current role at IBM, she served as Director of Accelerated Cognitive Infrastructure in IBM Research, leading a team doing cross-stack optimization of AI workload, optimizing the workload's hardware through software, producing productivity breakthroughs of 40x and greater, which were transferred into IBM product offerings. Hillery's technical interests have always been interdisciplinary, spanning from silicon to software, and she has served in technical and leadership roles in memory technology, systems for AI, and other areas. She is a member of the IBM Academy of Technology and was appointed as an IBM Fellow in 2017. ISCA'21 is very pleased that you are here for this keynote speech. Audience, please welcome Hillery to ISCA. Look forward to your talk on From Transistors to Enclaves, how architects have helped secure digital assets and healthcare records and more. Hillery, the floor is yours.
Thanks so much, Lizzie, and thanks to the ISCA audience. I know this is a different format than how we usually get together, and we had certainly intended to be in Spain all together. But as we go into the second year of virtual ISCA, I want to start this keynote with a little bit of a lighter note before we get into some of the technical content and the lessons learned. I spent a little bit of time looking at what the internet offered as tips for delivering a keynote. I want to kind of talk through some of these first. First off, find out what a keynote means. We're just going to go with a really simple definition here this morning, this afternoon, this evening, wherever you are tuning in from. The keynote at ISCA is usually the first talk of the day where we're all gathered together. Also, the second recommendation was to connect with the audience at the event. We are in a very different format. Usually, we would be speaking reverently of the past as we talk about the keynotes in the past, or a keynote speaker often tries to aim to say something so brilliant that everyone grabs those little pieces of paper and the cheap hotel pens and writes it down. I'm supposed to be up on a stage in a nice outfit, and I'm supposed to be showing that I can adeptly use that remote clicker. Also, they actually train us in classes to use very wide arm gestures. And today you actually get me sitting in the corner of my kitchen, and I'm trying to do little small gestures so that you can see a little animation as I talk. And of course, I don't get to have the really fun sort of rock star boom microphone that often comes with a keynote. So I want to take the opportunity, since we have such a different and an intimate forum and an opportunity to sort of converse with one another throughout this conference, I want to take the opportunity to maybe look at a keynote a little bit differently. So, in terms of speaking reverently of the past, I am absolutely going to do that, but we're also going to poke a little fun at ourselves throughout this, as you've hopefully just seen in the tone. And I want to be a little bit more quick and a little bit more engaging in the format of how we do this virtually, because 45 minutes listening to just one person is really hard these days. Secondly, we're not going to aim to have you taking notes on a cheap little pen and pad of paper, but I'm going to aim to try to not say something that starts a Twitter war in the middle of this talk. But hopefully there will be a few things that provoke your interest, that lead to interesting follow-up conversations, and that perhaps can create some themes for some of the ways that we interact throughout the conference over the next couple of days. So, the last thing that the internet offered as tips for delivering a keynote was to write down 1 to 3 key points that expand on the main point of one speech. I started out with 4, but internet says 1 to 3, so I've condensed this down to 3, and we're going to go with 3 things. We're going to talk today about iterative refinement, which, if you'll forgive me, I'm going to refer to as stubborn refinement. And when I shared this term with the team involved, they actually didn't object to stubborn refinement at all. So we're going to talk about stubborn refinement. We're going to talk about, secondly, collaboration to accomplish holistic engineering. I'm someone who, as Lizzie said in my bio, throughout my career in engineering, I have always worked on interdisciplinary and cross-disciplinary type of topics. And the engineering and the capabilities we're going to talk about today, I think, are a tremendous example of a team that came together really to work cross-stack and find new solutions to traditionally hard problems. And the third thing that I'm going to highlight is having a clear-minded focus on use cases. In conferences like ISCA, we really often are responsible through the paper review process and such to examine the minute details of the engineering, assume that and assure that the technical simulations and such have been done in the right way, and that we're predicting that techniques will have an impact and a change on processor efficiency or system outcomes or total security of an environment. But I think I want to take a little bit of a step back since I get to work in an industry lens and look at the use cases of really where architects, system engineers have worked together and collaborated with a single-minded focus toward the outcomes of how someone might use a technology. And hopefully this will provoke a little bit of new thinking in how we think about and how we potentially converse about the things that we each stubbornly work to refine each and every day. How do they actually turn into something that's usable by folks around the globe? So what are we here to talk about? Lizzie gave the title of my talk, which was From Transistors to Enclaves, How Architects Have Helped Secure Digital Assets, Healthcare Records, and so much more. But let's first talk about what enclave means in this context. When I picked the word enclave, I was referring to the space of trusted execution environments that are defined for confidential computing. Now, I know that there are papers here at ISCA this year about confidential computing. It is what some of you live and breathe every day. But in this community, we also have people that are worrying about the future of high bandwidth memory, and many other topics that are not necessarily directly in the security space or in confidential computing. So since I can't take that sort of ballroom show of hands, how many people need me to define a TEE, forgive me if this is the area that you study each and every day, but I want to kind of go through the definition and set the context for confidential computing before we go too much further. The Confidential Computing Consortium is a multiple party organization that publishes things like the deep dive document and works on standards for confidential computing. This is excerpted from their deep dive document, section 2.1, and they define confidential computing as the protection of data in use by performing computation in a hardware trusted execution environment. You can dig more into it to understand this more, but when I'm speaking to a non-technical audience, I like to try to compare this to, for example, a skyscraper. And if you'll forgive the simplicity of the analogy, in a skyscraper, there's security outside the building. There's perhaps a security desk at the front of the building. They check people's badges. When you go to get into an elevator, there may be, in some countries, even biometrics that are used to identify who you are, or again, maybe you use your badge against a badge reader. When you get off the elevator at a certain floor these days, again, you usually have to authenticate to get into the workspaces on that floor. And then you're in an environment where there's a lot of trust. There's auditability of who came in and out. There's recorded history that's archived of who came in and out. And there's a lot of trust, perhaps even background checks in some working environments that happened in order for someone to get from outside into that sort of trusted workspace. In an area like cloud computing or an on-premises IT environment, there are also similarly all those checks. There's security on the outside of the building. Electronically, there's a ton that happens in terms of identity and access management, authorizations, and privileges once you land on a computer ready to do your work on a virtual machine. But confidential computing really is about creating yet another degree of confidentiality for when data or code is in use in computing. And I liken this in a skyscraper context to saying we're going to go yet another level and walk into an office with a closed door, no bugs, no access to that office. and conduct business in that office in complete and total confidence, protected even from the rest of the parties who were safety checked and badge checked and such in entering into that office building in that floor. Now, my team likes to break down that analogy and point out different ways that perhaps someone could get access to what was going on in that office. Maybe there's glass walls around it. Maybe someone has a phone in there and has intercom system. But if you take away all of those potential breaches of that scenario and just think of it conceptually, in confidential computing, we're talking about creating complete and total privacy as well as authority over compute when it's happening even in a multi-tenant environment where there are lots of others around. It is sort of the highest form of protecting what you're doing. And in the context, it can either be on premises or in a cloud kind of environment. I want to propose, however, a new subtitle to this talk. I'm going to do what I promised in the abstract and in the title and talk us through a journey of how we have gone from transistors through to secure enclaves or trusted execution environments, and a little bit of the history of how this technology has come together, because I think there's a couple of important and interesting lessons. But I want to offer a new subtitle, which is thinking about how to beat the hype cycle. I know that sometimes in talks, the hype cycle shows up again, but just to make sure we're all on the same page, definition from Wikipedia here, showing the hype cycle as this curve with 5 stages that talk about maturity of technology. This is a technique that's used by analysts and especially by Gartner to represent maturity of a technology, to represent it being adopted, and to represent the use cases and such available. If we zoom into that curve, the hype cycle's 5 phases are depicted by this huge up and down motion. At the beginning, there's a technology trigger. Some technology is formed, some capability exists. This is often well after we as an architecture community have begun to think about and write papers, usually more where there's an actual embodiment of the technology available that's functioning and working. But there's a peak of inflated expectations. We go through this as a research community as well, where we have floods of papers. We're going through a very active period of exploration, attempting to understand what something is most useful for and how it can best be applied. Following that peak of inflated expectations, there's this trough of disillusionment where there's a lot of adjustment and understanding of what something is useful for. The slope of enlightenment is sort of that persistence of a few people and a few companies that push through, enabling something to be used more broadly. And then the hype cycle shows the plateau of productivity, meaning those technologies that we all in our daily lives take for granted, that are used and adopted broadly, and that have very clear and well understood use cases. Confidential computing, despite having a well-formed consortium and collaboration and set of companies collaborating together on it, and despite multiple products being in the market at this point in time, has been rated for the last 2 years on the Gartner hype cycle for computing infrastructure at the very beginning, the far left of this curve. And what I'm going to show you today is actually a full suite of capabilities, up to 16 terabyte of memory capacity, full databases, hardware protection through secure hardware security modules, et cetera, and use cases from healthcare to protecting consumer records to financial services and digital asset custody. Things that we all as consumers use each and every day are in production using confidential computing technology. And as I looked at this and I looked at this theme for this conversation, I think you could be so bold as to say that this team and this work has really beaten the hype cycle in the sense that this team has been able to demonstrate productive production use cases for a technology which a lot of people in the industry are still considering to be early. So I think there's an interesting story here to extract out, and those are the 3 points that I wanted to bring up to encourage us as engineers, to encourage us as an architecture community, to think about our persistence with topics, to think about iterative refinement, and to think about use cases so that all the pieces of technology can line up and do something interesting and have real world outcomes like protecting patient healthcare records. So item number 1 that we're going to talk about, what does it take to beat the hype cycle? It takes iterative refinement. I heard a talk from a professor at Tuck, which is the Dartmouth School of Business, a couple years ago that strongly influenced my thinking about innovation. This professor was talking about innovation fundamentally means doing something that no one has ever done before. When we score papers for ISCA, there's usually some form of a question, which is, how innovative is this paper? Is it incremental? Have I seen it before? And we kind of consider a highly incremental paper to kind of be the kiss of death in terms of a review. A review and a paper which appears to be a minor incremental improvement is usually not necessarily viewed as something worthy of top flight publication in a premier venue. And I'm not questioning that standard at all. But what I want to talk about is the methodology behind iteratively refining things. This professor in his talk about innovation basically said, if you envision that innovation means doing something which no one has ever seen or done before, think of it, for example, of trying to take a team, a startup, a research group, a development team, a set of developers. Think of it as basically trying to take them to the moon. You set a goal which no one knows how to get to. If we knew how to do it, there wouldn't be research, there wouldn't be innovation involved. It would just be a process of engineering. And what he suggested and what he proposed is that when setting an audacious goal, when saying, hey, we're going to go to the moon, think of the team process as there's sort of a plot, an XY plot. And in that, there's a couple of points known about how you might get to the moon. And as a team, you need to have a conversation that you're going to set a trajectory toward your destination, taking into account those points which are known. But that trajectory in and of itself is a hypothesis. It's a particular direction. It's a way for us to architect a technique or set up a simulation. It's a way to begin to move toward the moon, but yet the outcomes are not known. And actually, the field of data points is very, very sparse. There aren't many on the XY plot when you begin that journey to the moon. And what this professor encouraged is that a team have very open conversation about when their assumptions have changed. What if any of those original data points about what was thought to sort of scientifically or architecturally be true, what if any of those points were wrong? He encouraged a team culture where you get to question those hypotheses, where you get to reset that trajectory, where you get to pursue a different path, and where as a team you have a continued conversation about what all is known to be true. And I'm going to refer to this here in this journey of this team toward confidential computing as stubborn refinement. What I mean by that is if I look at the history of what has become these products and services and confidential computing technologies that I mentioned before and that we're going to talk about the use cases for, the story starts all the way back before 2001. For me, it started back when I was in graduate school and I met some of these people when I was doing an internship. This team first created a set of capabilities that enabled trusted execution in hardware environments. There was a gap, as indicated by that red box, of a good number of years when they then created and shipped a second set of capabilities. And then there's a gulf of time, which I refer to as the period of stubborn iteration and hypothesis testing, system architecture, integration, more chips, and more use cases that were validated, until actually the first products began to appear. First appeared in 2017 on premises, on 2018 baked into use cases in the cloud, then the Confidential Computing Consortium was formed, and then further capabilities were put out in time. And as I asked this team how they sort of viewed the last 20 years, the 4, 5, 6 generations, depending on how you want to count it, of this technology and its maturity, they broke it into the phases shown along the bottom. Initially, they talked about the plausibility phase, but in plausibility, they did really hard work. They actually released chips, they released full systems using these technologies, and those initial things weren't just flimsy ideas. They were actually manufactured things that shipped and actually shipped out into things that many of us have interacted with over the last 2 decades. They then referred showered to a prototyping phase. They didn't assume they had it right. Even though they had gotten to ship these security features into products, they remained persistent over a long period of time. And then as they began to see the market opportunity arise, and we'll talk about exactly what that is, they started shifting what they were doing. They worked more with systems architects, they worked more with the firmware teams, and they ultimately ended up working with cloud services teams to take the kernels of the architectural ideas and the security architecture that they had done all the way up into the stack. And so that leads us to the second point that I want to make. The second is collaboration to accomplish holistic engineering. What I mean by this is when we talk about things like cloud computing, we use terms like containers and such that actually allude to architecture principles. If any of you watched what happened in the Suez Canal recently with the Ever Given container ship, you saw how important it is that the base of a container ship, the ship itself, be a stable foundation for everything which is precariously stacked on top of it. The height at which containers are stacked in a physical shipping environment is absolutely astounding, but there's a tremendous amount going on. Number one, those containers are standardized format. Number two, there's security. Those containers are secure and they're secured to the other containers. Number three, there's extensive planning of how the containers get onto the ship, how weight is balanced. And number four, there's that stable substrate. The ship itself is well balanced. When this gets out of whack, this is an actual picture of a ship referred to as the MV Rena, which actually ran into some coral outside of New Zealand a number of years ago. Losing that stable substrate starts to cause the entire architecture of the design to begin to break down. And so successful architecture in everything we do, but especially when you get into things like cloud-based computing, where what's exposed is sort of an API-driven service, but underneath that, the layers of the application, the operating system, the firmware, the secure boot process, the hardware security modules, all the way down into the transistors, need to be formed into a holistic architecture. What I mean by this is, traditionally, we have often talked a lot about protection of things in terms of moving data, the techniques and technologies needed to encrypt things while they are in motion or data is in transit. We've also talked a lot about the bottom of the chain, technologies to protect data at rest. Any of you who have worked in storage will be very familiar with cryptographic technologies or solid state drives. It's always important to protect data at rest, and we are all very conscious of that in our daily lives as well. But confidential computing questions, hey, this is not really kind of a complete picture. We need to also look at when data is being used. This is what the industry and the consortium refers to as confidential computing. The protection so that a user has full privacy and authority over their data when it is in use. But this actually needs to be a full chain. And one of the observations of this team was that there needs to be a chain of technologies going all the way from moving data to an environment, using data in an environment, and then protecting data when you're not using, meaning it's sitting around in sort of a cold state. This all needs to also be backed by the picture depicted on the left there, which is key protection technologies, meaning having control over the cryptography that's used to protect the data. Now, I have attempted in this talk to avoid a lot of sort of branding references and such, but at one or two points, it's going to be kind of inevitable that I need to kind of throw out some marketing terms or some branding. But if you're curious, you can see some of the different services that encompass this full space and spectrum that are available on IBM Cloud in terms of what, from a marketing perspective, we call the HyperProtect family of services or the Data Shield services. But all that being said, this team that worked for many years, and frankly, 20 years, 4 or 5 different technology generations, was actually working in many cases on individual little pieces of this whole picture. And I said before, the important part of this segment of the talk is to talk about holistic engineering, to talk about cross-stack, and to talk about taking the big picture into account. So let's look down first at the transistors. We don't have time today to go through all 5 of those boxes, from key protection to data in transit to data in use, and then into data at rest encryption. And some of those areas I think are understood much better than others. To lean in a little bit on the key management side, as an example of really stubborn and iterative refinement, I think it's important to talk in this situation about the hardware security module. This is where we go all the way down into the transistors and into ASICs, into cards that are built, and will build up into a system. A hardware security module has a general purpose computing environment that has to be robust against physical and logical attacks. It has to run the intended software, and the users of a secure hardware security module have to ensure that the software has not been modified. You have to be able to remotely distinguish between the real device and a clever impersonation. And in addition, you have to remain secure, even if an adversary carries out destructive analysis of one or more of the devices on this hardware security module. The reality is that today, computing is a very distributed kind of a function. When we design something as architects, who knows where it's going? Some of us are working on things at the edge. Some of us work on things that will go into computers that sit on premises or in a manufacturing floor or a retail outlet of a bank. And some are working on things that are destined for cloud. In these different environments, there's an increasing lack of trust of who's physically around. And so it's important, as this community has considered in the past, things like even the sort of famous work of taking memory and cryogenically cooling it and being able to determine what the bits on it are. It's important to consider and continue to consider also physical attacks against hardware. We may have done all of the logical design of something, but the physical attack needs to also be taken into account and architected into the overall system design. In this program, a secure hardware security module, a custom hardware security module has been built. And this custom hardware security module has tamper sensing and responds to tampering. Specifically, if physically tampered with, the contents of this hardware security module are zeroed out. And this means that it is designed with protections against a wide variety of attacks that have to do with everything from side channels attacks to power manipulation, topics discussed extensively in this community, but extending all the way into temperature manipulation and physical attacks against the card. So in this card, a lot of different technologies and techniques have been brought together. Really, you can kind of think of it as what would have been many different papers have been coalesced together into a single hardware form factor. The important thing is, however, that this provides a lot of cryptographic function, but it provides the ability to hold the keys that protect data in an incredibly secure fashion, meaning that not only can things be cryptographically protected and such, leveraging the ASIC that's contained on this hardware security module, but people using this security module can be confident that it's secure, even if it's not on their own premises, because of those tamper-proof capabilities. The ASIC inside of this hardware security module, you can see a few of the statistics here, but it supports several hundred cryptographic algorithms, including symmetric and hashing algorithms, as well as asymmetric algorithms of various types. This has, DDR4 memory interfaces, PCI interfaces, et cetera. And all of this comes together into systems where the techniques and technologies of that stubborn determination and the stubborn set of architects at the root of this are now able to provide trusted execution enclaves that have incredible memory footprints, up to 16 terabytes of memory. No code changes are required to run this in a Linux environment. And these systems are capable of running large enterprise data workloads, high transactional throughput workloads, and things that usually when we begin that kernel of architecture work, we can really only dream of. How does this come together? Well, the different sections of the system that are sort of highlighted in red there refer to the processing facilities. That's where there's been work done on custom memory systems that enable that really large memory footprint. And those I/O blocks are the cards and the hardware security modules that I depicted earlier. And the different components of the system start with the transistor level design and the ASICs, build up through to creating a hardware security module, which is tamper-proof and therefore gives confidence that even physical attack does not compromise what we're trying to do with these type of systems, builds into running key protection in a dedicated trusted execution environment, and the trusted execution environment or secure container facilities that provide the vertical and horizontal isolation so that people know that they're effectively coming into that office building. There's tons of security all around it. But for the work that has the highest degree of sensitivity, they can do so in sort of a private office and know that they are the only one with authorization over their code and over their data. They're also the only ones with control over their keys, and the keys are robust even against physical attack because of those technologies that have all been brought together that I was discussing. So I want to spend the last 15 minutes that we have here today talking about having clear-minded focus on use cases. The technology and the statistics are really astounding. This is, something like 100,000 times, more capable in terms of memory footprint than other technologies, that are on the market. Those kind of statistics come through that stubborn iteration. Those kind of capabilities come through a team of architects who have been willing to work outside of their boundaries with folks in the security space, been willing to work with system architects, been willing to work with cryptography teams, et cetera. But to me, most importantly, they've been willing to do so in a context with a very clear-minded focus on the use cases. Thinking about, if I come to work today and I work on my security architecture component, I work on secure and trusted boot, I work on whatever my topic is in this space, how is someone going to use it? And how do I therefore need to adjust? Is this going to potentially be usable in an environment that requires lots of throughput or has a lot of transactions? Is this potentially going to be something that at the end of the day will have a lot of latency sensitivity? The number of engineering trade-offs in this whole space are enormous. We each face those kind of things as engineers and researchers in our daily work. But keeping a use case in mind, I think, can be particularly helpful to help us make those engineering trade-offs in the best possible way. So I want to talk a little bit about the factors at play. As I mentioned at the beginning, we're in such a strange environment these last couple of years. But for the companies that we as consumers work with each and every day, the rate and pace and change demanded on each of them has been tremendous. Probably all of you have switched to completely digital banking. If you weren't before, you have perhaps even helped family members make that transition in the last year and a half. That causes a lot of change in the back-end computing infrastructure of the companies that we as consumers use every day. This means that things like latency expectations, bandwidth, the interaction of applications with the compute hardware have all changed significantly, and people have had to stand up new workloads in the matter of weeks. We got to work with a company that had to establish their country's equivalent of what in the United States we called the payroll protection program, and they had 6 weeks to do so. This is a major enterprise application that had to be stood up in a very short period of time. And so if we look at the factors in play in the industry as a whole, there have been increased pressure to digitally transform, create new applications. There's been a significant change in workload volumes. Some things have gone tremendously up. Some things have fallen through the floor and have gone tremendously down. You can summarize this saying that there's a lot of need for elasticity in computing these days. There's also a greater desire for cost efficiency. Many different types of companies are struggling with their budgets as they look toward recovery in the current environment. And all these paths do point in sort of sum to cloud value propositions. Cloud has exploded over the last 18 months because it's a place where different types of compute, different architectures, different memory capacities can be made available, different accelerators, et cetera, can be made available, can be consumed and tried and tested out. Cloud is this tremendous playground in some sense for what we all do as architecture work. But on the flip side, from an enterprise and a business lens, all of this drive toward increased cloud consumption has led to an increasing set of concerns and discussions on security. Security business is booming, but when we look at what it takes to recover, for example, from a data breach, the cost is tremendous. We all know this is an important research topic, but a typical enterprise recently was measured as taking an average of 185 days or so to recover from a data breach. You can assign some sort of millions of dollars that it took to do that cleanup, but the economic impact of taking 6-7 months to clean up from what happened is tremendous and is something that businesses right now just can't afford. So what we do down in those transistors, what we do in cryptography, what we do in creating secure boot, what we do in creating hardware security modules, what we do in creating those architecture capabilities and the hardware capabilities that are tamper-proof, robust against side channel attacks, each and every day has a concrete outcome on how businesses can ensure that they can move forward and can recover from the current environment they've been in. When people are looking at consuming things, especially in a cloud, it really is that analogy of a skyscraper. There's lots of people around, and people need to look at end to end. How is data getting to that environment going to be protected? How is data and code going to be protected when in use, confidential computing? And how is data going to be protected when it's at rest and when it's stored? When we look at a few surveys that have happened, this is very recent data. This is from December of last year into February of this year. So very much sort of in the present era. One of the common questions that was asked here by this company, Pulse, that facilitated this survey is, who are you focused on preventing from accessing your data? I think those not working in the space naturally think of cyber criminals. But if you look at what enterprise leaders were pointing to in the last several months, there's increasing levels of concern coming about staff and employees and their third-party vendors, including in some cases also their cloud provider. If you look at how they're looking to protect data, the question, which of the following confidential computing security benefits would positively impact your organization the most, you can see that the capabilities, or sort of the hills stated here, range everything from protecting an organization's own data to securing data that's used in multi-party information. You know, there's a lot of work going on, for example, in federated learning and AI and things like that in the technology space, for protecting data that's being shared between organizations, and protecting data as well against those who hold the data are key things that everyone has first and foremost in their mind. So when we think about use cases, fundamentally what's happening is that companies are looking at their data classification. We don't in this community tend to talk too much about things like regulations, but just to share a little bit about how this ends up turning into an important use case for these kinds of technologies that this community is exploring, and things like confidential computing and side channel attacks and all those things. What happens in an enterprise is that they look at classifying their data. We all see this sometimes when our personal data is used on a website and we have to agree to certain types of terms. But in the back end, usually an enterprise has a notion of a wide span of data, everything from fully public data, which everyone could have access to, internal data, which is a little more sensitive, confidential data, and ultimately sensitive data. The more regulated an industry and a company is, something in, for example, financial services, every country around the world, even though the fact that there are differences in some cases around regulation of personal information or healthcare data, every country around the world regulates their financial system. Why? Because they want to ensure that their economy is robust and can keep functioning. But this ends up translating down into a set of requirements on the computing, the compute substrates, and the security of the computing that can be used for things like sensitive financial information. So as we look across this span of data classification, we would suggest that operational assurance, all of that sort of checking of badges, the auditing of the video cameras of who's kind of coming in and out of the building, are absolutely necessary. You don't want to have a breach on even your internal information. But as you move into more confidential and sensitive applications of data, the notion of technical assurance becomes useful. Operational assurance means, in a cloud context, that the cloud provider commits to not access your data. When you're using standard encryption at rest on cloud storage technologies, this is the commitment. It's in a contract. It is a commitment that's made by the cloud provider, and you can and should trust them with your data. But when we're talking about the most sensitive data, when we're talking about the fact that people are truly concerned about demonstrating that they have full and complete control over their data, we have to get into a notion of technical assurance, meaning that the cloud provider, because of confidential computing technology, and the cloud provider, because of the way things have been constructed in the cloud, cannot access your data even if they are asked to. This provides that higher level of assurance equivalent to the work being done in a sealed off, dark walled office that is done in complete privacy and confidence, such that even the operator of the building security system doesn't know what's happening inside that environment. This transition then enables construction according to the sensitivity of data of a robust understanding of how things will be protected. Fully homomorphic encryption, for example, is a set of technologies that have been discussed here in this community. But as it is maturing, the opportunity to provide technical assurance on very large memory sets, leveraging tamper-proof hardware security modules, meaning being able to run full industrial size at scale, at speed capabilities, offers enough protection, even in those sensitive data classes, for data actually even also to move to the cloud. And this is where the use cases and applications become interesting. But this is also where every single corner of the overall architecture of the system has to have been closed off. And what I really see is the exciting part of this work. So I don't want to, in an ISCA talk, spend a lot of time talking about brands and logos, but I wanted to kind of just quickly share 4 different areas where we're seeing actual use of this technology and where I sort of come from in saying being able to accelerate the hype cycle and kind of beat the hype cycle in terms of adoption. One of the areas that we're seeing great use of confidential technology, confidential computing technology, is in financial services. As I mentioned, we all, as consumers, but universally the regulators of different companies' financial systems, acknowledge that financial data is really, really important. But there's another area that many of us are familiar with as well, which are digital assets, digital currency. And you can imagine that in that situation, having the highest degree of security data protection possible is something which becomes fairly obvious. In digital assets, though, there are fascinating things happening where this is not really just about coins. This is not just about currency. It's also about being able to transact energy contracts. It's about being able to create different use cases around fully digital transaction of for example, selling a house or some other physical asset. And those involve actually not just data at rest. It's not that you want your digital currency locked up and held really tightly, but actually you want to transact on things. You want to transact on digital assets. That's where data in use and confidential computing then come into play. In healthcare, I think we all highly value our privacy. We value the privacy of our healthcare records. And then with regard to wanting to protect consumer data, we all actually expect a high level of confidentiality. When we make a major purchase, like a car, we expect that that company holds our data secure. And this is where we pop all the way up to the top of the stack in terms of use cases. In the Apple situation, our partnership with them around these technologies with the Apple Care Kit has taken this project, this work from the transistors up through the application level, and put it instead into the hands of iOS developers who leverage something called the Apple Care Kit. Now, why does it matter? Why does someone making a healthcare app, a mobile app, care about what's going on in the cryptography and the secure boot and all those kind of things? Well, frankly, they don't. But these technologies that are built up supporting the applications that are deployed, that are developed with the Care Kit, actually enable the developer to very quickly accomplish HIPAA standards. And for those in the United States, HIPAA is the standard by which folks working in the medical space with personal confidential information are required to protect data. Basically, what has happened here is the stubborn determination of this team, the persistent refinement of the technology, and the holistic integration all the way up into the stack has enabled these architecture capabilities to be encapsulated and abstracted all the way up into an iOS developer kit that enables people to very quickly create new capabilities that also meet the HIPAA standards. This is therefore driving innovation. We're working with dozens of companies that are working in this space to very quickly create new health tech. This is, startups. This is companies that are being disruptive in how our healthcare information can be used, can be analyzed, can be stored, et cetera. And so a set of architecture technologies is now driving health tech. And I find that kind of thing incredibly exciting. Second example, in digital asset custody, I mentioned a little bit, why it matters, but the term of a warm wallet or use of a digital asset refers to something that then drifts into the space, not just of are my digital assets being protected and secured, but how are transactions around digital assets being used? And there's a lot of exciting things happening in this space. And lastly, the work with Daimler here is one that I consider really interesting because in the outcomes, you can see that they need high scalability, they need very high platform level resiliency. But at the end of the day, these architecture technologies have translated into them actually being able to make a commitment to their customers regarding their customers' information that was used during the sale, that they are protecting their customer information, financial information, address information, car information at the highest possible standards. And for a company, this then enables them to take those architecture techniques that have been worked up the stack, packaged into services that are consumable, and make a commitment to their customer that they are doing everything that they can to protect their data. And this is really about their trust with their customer base. So wrapping up here, just 2 more minutes and then we'll get to Q&A. One of the things that I didn't share with you at the beginning when I talked about, what the internet offered as tips for delivering a keynote is I didn't actually tell you what the internet said a keynote means. I just said, well, at ISCA, we consider a keynote to be that first talk where we're all together and we think about some sort of architecture topic. But keynote, according to the Oxford English Dictionary, the term actually originated as the note on which a key is based. So the key of C major, for example. Some folks pointed out that this is sort of the tone or the key that's given when an a cappella group, a group singing unaccompanied, is going to sing a song. They often start with a key that indicates the key they're going to be singing in. We now refer to that usually as a tonic in English. But in this context, there's actually a really interesting etymology, which is that it can be the prevailing tone or central theme for a conference. And there's a hobbyist or professional here that studies etymology that has a blog called Mast Radish. And I think this was worth sharing. So in the 1600s, the keynote referred to that first note, but in use of it in the English language, it refers to the main idea of a speech. It refers to the main idea of a conference. And is meant to set the prevailing tone throughout, just like it grounds a set of musicians in what they're about to do. So just in wrapping up, I want to go back to those 3 points that we went over and just propose a few things that these could mean for us as a community. Number 1, with regard to iterative, or what I'm referring to as stubborn refinement, I think there's a tremendous amount to learn in the fact that we've gone on a journey spanning over 2 decades, multiple publications, multiple releases of hardware. But there has been a tremendous persistence of this team in order to create those capabilities that now we as consumers can interact with, and where companies can assure that they're providing a high level of data protection to those who are using their goods and services. But when we look at this in terms of their collaboration to accomplish holistic engineering, I just wanted to give an encouragement. As we interact with one another over the course of the conference, I think one of the great blessings of COVID is that the question of how are you and how are you doing? How are your family? Those are no longer rhetorical questions. We expect an answer these days. We really do want to know, how are you and are you doing okay? But as we talk about each other's work, let's look at those problems that we are each working on day to day and stubbornly refining. Let's look at the work of others and what they're stubbornly refining. And I would encourage us to think about and explicitly talk to each other about how, if we took what one person is stubbornly refining with what we are stubbornly refining and brought those things together, how could we begin to build toward greater purposes in our work? And lastly, the clear-minded focus on use cases is therefore, I think, just a really neat lens that comes. It is a unique position of being in industry that I get to go all the way out and spend time with clients, and then we dive all the way down into the transistors and discuss the cryptography techniques that we're using and the hundreds of different standards and algorithms that can be accommodated. That's a unique value of being in industry. But many in this community are in academia, and I just encourage you to look out into other areas. Think about how your work could apply in edge and in 3G and what's happening in those spaces and transforming public services and healthcare and all those kind of things. Think about how your work might end up being used in a cloud or used on premises or in a mobile device. And really pull that thread and use that to focus your ideas onto techniques and technologies that are going to end up being as consumable as possible for the broadest audience. So with that, thank you for spending a really long time watching just one keynote virtually. And we're going to move into Q&A. My thanks to a huge team who has worked in this space for quite some time, and many of whom provided materials for this talk today. So Lizzie, I think I'll turn over to you to help field and moderate some of the Q&A.
Thank you, Hillary, for an exciting keynote, which talked about the many facets of secure computing and going from transistors to the software higher levels. So we have some questions from the audience. So the first question for you is, can a completely secure environment become a source of threat to security, as a completely secure environment can mean no regulatory authority monitoring the activity of the users? What do you say?
Yeah, I think it's a great question. And actually, there are a number of different considerations on this going on around the world. It's a topic actually that, to my knowledge, Australia is actually one of the first regulatory domains that's looking at this. I'm not an expert in sort of, the ethics in some of these areas, so I don't want to overreach in answering it too far. I think that it is an important question, but there is a really important trade-off to be had, right? There are such fundamental and important systems for our economies, for protecting individuals in the economies, et cetera, that it still feels like the right thing to do is to provide as capable of systems as possible to handle those appropriate use cases.
Thank you. We have another question relating the definition of confidential computing and TEEs that you showed from the Confidential Computing Consortium white paper. Can we question the definitions themselves? So this the person who asked the question says, I find it flawed in that it does not contain remote attestation. How can such a TEE be useful in the cloud scenario where one has no guarantees on one's code and data with remote attestation?
Yeah, so I think it's a great question. And just to be clear, the Confidential Computing Consortium is really trying to tackle refinement of the data in use, or I would say also code in use, Enclave, the trusted execution environment. But I think you're pointing out an important thing that I meant to convey kind of in that showing the chain, where I talked about data in transit as well as data in rest. The process of secure and trusted boot, the process of attestation, all those other kind of things absolutely need to happen. And if you look at the chain of things in the chain of trust that needs to happen to end up with a trusted execution environment, many of those things are included in what must actually happen in order to land in an environment which is trusted. So some of those sub-techniques and some of it's outlined in that deep dive paper are actually discussed by the consortium and presumed to be in place in order to get a trusted execution environment. Some topics are actually adjacent and we think actually need to be considered. So I argue sort of more for a confidential computing plus definition of things. And when you do security architecture for deployment, you do need to consider those adjacencies, not just only the TEE.
Thank you. Another question. This all looks so good, but there have been a bundle of attacks on TEEs. Besides, we found inconsistencies within the specifications of Intel SGX and TDX. What's your take on that?
Yeah, this is an area where, the role of the architecture community in, questioning things and testing things and such is really just such an important environment. I don't want to, speak necessarily to, specific things about one technology or another, but I do think that it's important that there be open conversation about, how use cases and what the security envelope of particular solutions and technologies are. The technology that I was showing is based on IBM's hardware and software and firmware and operating systems work and such like that, and has been shown to be trusted at scale, also for large memory use cases as well. So the technologies that we're doing are a little bit different than some of those that were mentioned and that have been studied by some papers in this community.
Thank you for a great talk. Is there an example you could share of how the security architecture was refined based on feedback or iteration from a holistic view? Is there an example you can share?
Sure. Yeah, I'm happy to do so. And I need to anonymize it a little bit. But one of the things that we've been talking about in our research community at IBM has been the scientific method. And there are some materials out there from the director of research, whose name is Dario Gil, actually a Spaniard, and I guess I'll mention a Spaniard here in honor of our virtual location here. But Dario Gil has, some recent talks out there about the scientific method and how, as an organization, he's encouraging everyone to kind of take a step back and think about that scientific method, even when we're doing what we would normally consider engineering projects. To describe that a little bit of what happened over the course of this technology. First off, the architecture team working on the original techniques did full chip writs. So number one, they actually did that work of going all the way through to chip writting. They did a lot of work around penetration testing and other standard techniques, some of which are used and have the prior question alluded to an author that's kind of working in that space of finding security vulnerabilities. But most importantly to me, about 5 years ago, they did their first actually fully stood up end-to-end system with a real client, with a use case. Again, in industry, we have that luxury and we have that opportunity to say, okay, what is the type of workload that you might need to protect in this way? In that case, it was something in the area of risk calculations. And they did that work to end-to-end go from a customer's on-premises environment to a cloud computing environment with these techniques stood up from the chips all the way up through the systems and the cloud services. And they iteratively refined and worked through the entire stack. So I guess if I was to take a step back, I would say they each, within the scope that they were able to work in, did that stubborn iterative refinement at the chip level, at the architecture level, at the system security testing level, and then in the full integration, working through the steps and the scenarios. As the prior person asked about, at a station, wait, what happens? You only get to those questions if you really try to at least run a simulated scenario end to end of how is someone going to try to use this technology? What is the type of code? What's the type of data? What are the requirements in performance and throughput? What are all the different stages where there are handoffs across data? And they work through that from an overall system engineering perspective as well. So, I know, again, not everyone is going to be able to work through that full system engineering on the architecture work that they're doing. We can approach much of that in simulation, right? But in working in the space that you're able to control and continuing to iteratively refine, take a step back and think through as a user what's actually going to happen. I think those are the situations where the greatest amount of insight and progression in this work happened, to my impression.
Thank you, Hillary. Actually, there are many more audience questions. However, the time is up. We only have half a minute left. So I am going to take this opportunity to thank the speaker and thank you so much for delivering this keynote. What I will do is I will take I'll copy these questions down and I'll send them to you and we'll figure out a way to answer some of them on the platform.
Absolutely. And please feel free to reach out offline as well for anyone who wants to do the virtual version of when I would step off the stage and we would have a coffee break and I would chat with you. Please feel free to reach out offline as well.
Yeah. Thank you so much. That was a great talk. Thank you.